with where we left. And here there's only 39 of you now. I think there's 43 now. Gosh. So Sierra, tell me if you can see the presentation on the screen. Sierra? Sierra?
Yes, you can see the screen.
So Moses has
Yes,
taken
yes,
off.
we can see.
Moses, what are you doing? Okay, so in the last class, we were talking about the log amplifier. We were talking about the log amplifier, which is a special type of amplifier, whose output is the log of an input voltage input to it. And we saw some of the applications that normally used in analog amplifiers, that normally used in instruments with log indication. They're used in recording studios for compression, so that the signal can fit within a certain voltage limit, or we call it the dynamic range of the channel. And so that once it has been fitted, and then we can expand it. I think most of you guys, I don't know whether you are born or not, but the time when there's the craze about cassette music, well, music, that's before the advent of CDs. CDs was a recent invention, so all the music, most of the music were either stored in vinyl plates or CDs. CDs was much more cheaper and more easier to transport because it was more compact. Also, to transmit signals through television, those days, the recorders were tape recorders. So both the audio and the video were recorded in tapes. Now tapes have got a very limited dynamic range. So we had a lot of noise reduction techniques which were employed by companies. Okay, so like there are so many companies producing high quality sound systems, like those ones for movies. So Dolby invented a system. Dolby is the name of the engineer, invented a system called Dolby A, Dolby B, Dolby C. So Dolby C was the highest performer. Dolby B was a bit cheaper. So most of the high quality cassette decks that you'd find in the homes, they used a compression technique known as Dolby B compression. For studios and cinemas, they'd use Dolby C, a compression, and then expand it later on with the either Dolby C expander or a Dolby B expander. That's because the tape, a normal tape, which are normally made of ferrous oxide, we had about 3 levels of tape. There was the brown tape, which was normally ferrous oxide tape. Then there was the chromium tape, which had a slightly higher dynamic range. The normal metal tape had a dynamic range of only 55 dB, means the maximum signal to noise ratio was only 55 you could get. With the chrome tape, you could get almost like 60, 62 there. And then there was metal tape, which is even more expensive to buy. You'd get maybe around 65 dB. Now, to improve the quality of the normal cheap tapes that you could buy in the shops, you had to use Dolby B compression and then expand it later on. Nowadays, you don't see those systems because the CDs came and took over. Because of the CD, if you record music or you record maybe video inside a CD, the signal to noise ratio is always almost 70 dB. So it killed all those systems. Okay, so that's the practical side of things. Now let's get into the class. So we were considering a practical log amp in the last class. The practical log amp. Now, I don't know why I lost my notes, but I managed to edit it again. So I hope you can see it over here. This is the practical log amp. I hope some of you are doing this in the class, in the lab class. This is the only circuit that you can do. This is one of the only circuits you can do in the lab. All the other ones are theoretical because it assumes so many things that the devices are ideal. They assume that everything is ideal. But when you go to the lab and try and make them work, they won't work. So this is a practical circuit. Okay, so I hope I've squeezed it here. I don't know if you people can really see it. I'm just seeing how to expand this again. Okay, let me just do this. Anyway, I won't waste time. I'll just talk about it. I hope you can see. Let me try again. Excuse me. I think now that one is at least a bit light. So this is a practical log amp of the type which you can use in the labs. The reason being, most of the op-amps that we have in the lab, they'll suffer from large offsets. So this circuit, they have null offsetting circuits. So for the first op-amp A1 over here, you can null offset it with this potentiometer P1. So P1, if it's halfway in between, then the voltage going to the 10 mega ohms resistor is 0. Okay, but now to null offset the circuit, because I told you the op amps, even if you ground the two inputs, there'll be some voltage that appears at the output. It's called the output offset voltage. So you can null offset it. If it's greater than maybe positive a few millivolts, you can change this potentiometer P1, say that the output is 0. We shall see later on. So we've got this circuit towards the left with the potentiometer P1 and 100 mega ohms. This is a null offsetting circuit. Just supposed to provide a very, very small current to balance the two inputs. Because we said that for the op amp, the first two inputs is a differential amplifier, and the transistors may not be exactly identical. One might have a slightly higher current gain than the other. Another one might have also a slightly slightly different VB characteristics. So if you bias both even at 0.6 volts, one might pass a higher current than the other. So P1 and the 10 mega ohms and the other potentiometer, which is connected between plus 15 here and minus 15, is a null offsetting circuit. Similarly, for A2 over here, the null offsetting circuit is this potentiometer, which is 100K over here, connected between plus 15, minus 15, and this 1 mega ohm resistance. So we shall see what they're used for later on. Okay, so most of the circuits that we draw an op amp without these circuits, those are just academic circuits. In the lab, you'll have to take care of the offsets of the op amps. Okay, so this is the practical op amp. It's practical because we can cancel the effects of offset voltages at the output with the null offsetting circuit. Okay, so this is the circuit we're dealing with. So I've just magnified it over here in this page. And then we'll go back to the notes. This one. Okay. So this is just the same circuit. This is the same circuit I'll be talking about. Okay, so to analyze this circuit, wow. Let me go back to the bigger one. That's the last one, okay. So let me just give you an idea of how you're going to analyze this circuit. So if you look at the output of A2, look at the amplifier A2, there's an arbitrary voltage here called V as its inverting input. Now this 29.5K resistor, in my notes I've called it R4. This feedback resistance, I'll call it R4. So for the op amp, we know if this an inverting input, I'm talking about A2 now, is at V, then this is what we said in the last class. On the positive side, that potential should also be V. So I can relate V to V naught. So we can assume that this V drives an arbitrary current, maybe I, over here, and this current must come through R4. Therefore, V naught is the drop across R3. So V naught is the drop across R3 plus the drop across R4 to V. So If we take KVL to that path, you'll get V naught is equal to V, which is the drop across R3, plus I into R4. Or we can write it as equal to V I, you can write it as V divided by R3, because the drop across V, the drop across R3 is V, and therefore the current flowing through it is V divided by R3. So we can write that V naught can be written as V into 1 plus R4 over R3. I don't have space for the brackets. So that would be the first step. So it means that if I can determine what V is, I can determine what V naught is. Now to determine what V is, I'm going to apply KVL to loop ABC. A is the input of Q1. B is the emitter. And C, which is not very clear there, is the base of Q2. So to determine V, all I'm just going to do, I'll start from A, drop across VBE Q1, because the voltage across here, I'll call it VBE1. And the voltage here is VBE2. These are positive, negative. These are positive, negative. So I can get an equation if I start from, so I'll be applying KVL to loop ABC. So I'll get minus VBE1 plus VBE2 should equal to V. So next I'll have to determine what is VBE1 and VBE2 with respect to the circuit parameters. So I hope that is clear and everybody can follow. Is that okay for everybody? I hope that's okay for everybody. Now, let me just go to my notes because time is not on our side. It's actually very easy. So you have to find out what is VBE1. Go to determine what is VBE2. Once we know that, we are substituting this output equation over here that we note is V into brackets 1 plus R3 by R4. Now in the notes, I'll be using the current through the first transistor as IC1. Or I think sometimes I'm calling it I1. I'll check in my notes. And the current through the second the collector of the second transistor, I'll be calling it IC2. Or maybe I2. I'll check in the notes what I've used. Now from this circuit, let me just give you a hint. IC1 is the collector current through Q1. IC2 is the collector current through Q2. Now, we'll use Eber's equation for the current relations between current voltage relation for a transistor. So for a transistor, IC is I naught e to the VBE over neta VT minus 1. So this tells me IC1 will be I naught 1 into E to the VBE 1 over neta VT minus 1. Remember we said that neta is 1 for germanium transistor, neta is equal to 2 for silicon transistor. Now in the transistor area of operation, once you've passed the cut-in voltage, you normally find that VBE over neta VT greater than 1. So we can approximate that IC1 can be written as I naught 1 E to the VBE over neta VT. Or we can write that IC1 over I naught 1 is E to the VBE over neta VT, or we can take the natural logs of each side. The natural log IC1 I naught 1 is VBE. So the VBE is 1 if you're talking about the first transistor over neta VT, or we can write that this implies that VBE1 is equal to neta VT natural log IC1 for I naught 1. And similarly, we can say that VBE2 will be equal to neta VT natural log IC2 over I naught 2. I naught 2 is the reverse saturation current. So there is where we are. So now let's go back to the notes. I think those are the only two difficult things to remember. And then just before I go back to the notes, if you look at this circuit over here, IC1 will actually be the current that passes through here. Because the biasing circuit, the null offset circuit, the impedance is very high, passing through the 10 mega ohms. So IC1 will go to the collector. So that the current, if I call this current passing through R1 to be I1, then I1 will be our IC1. Because we'll assume our op-amp to bias it requires negligible current. And since the other side of the op-amp is grounded for A1, the minus side of A1, input side, is a virtual earth. So I1 is just simply equal to Vs divided by R1. So these are some of the results we'll be using. Okay, the S doesn't look very good. Let me just run it a bit. There's Vs divided by R1. Similarly, I2, if you look at the collector, the collector of Q2, if you look at the collector of Q2 over there, here we'll have to make an approximation, which we'll deal with in the next example. So if you look at the current that is passing through this R2, the current that is passing through R2 accurately, I'll call it I. R2 is actually equal to VR minus V all over R2. If you had to determine it accurately. So here we'll have to make an approximation for this circuit over here to simplify our analysis. Now, if you look at this amplifier A2, the feedback resistance is 29.5, which is R4. And the resistance connected to the ground is R3. So the gain is approximately 1 plus R4 over R3. Which will be 29.5 divided by 0.5. If that was 30 instead of 29, it was 30 divided by 0.5. That's 6. That's 60. So for this particular circuit, the gain is approximately, for the output stage, is approximately 61. So if you assume that the maximum voltage, if you assume that the maximum supply voltage is plus minus 15 for the op-amp, it means the output voltage cannot exceed positive 15 volts, because the maximum the output can climb on the positive side is 15. The maximum output voltage of A2 can go the negative side is minus 15. So if you divide 15 divided by 60, is 0.25 volts. So with 0.25 volts at the input V, the circuit saturates. The op-amp is overdriven. And if you're not operating the op-amp at its extreme limits, if, for example, we are only using a maximum of, say, 5 volts, then 5 divided by 60 will give you 0.08 volts. So V will be approximately 0.08 volts for us to get a peak-to-peak of 5 of 5 volts. So to make life easy for us, for this first case over here, we'll just assume that V, for all the areas of operation of the output, is a small value. And therefore, IR2 is approximately equal to just VR over R2. Approximately equal to VR over R2. And then we make the assumption again that the transistor Q2 has got a beta which is very, very high. So the base current, which is required to form the collector current, is negligible with respect to the collector current. So this IR2 is the same as our collector current. And of course, to bias our op-amp A2, current is negligible. So that's the only assumption we're going to make in this analysis, but later on we shall correct it in a better designed circuit so that we don't have to use this approximation that IR2 is approximately VR over R2. So with These few points, we can go directly now into the notes. I've used the same equations over here, but here I'm just showing you how I've gotten those equations. Okay, so this is the circuit which we're using. I know it's small if you're using a laptop, but I've shown you how everything is gotten. So to analyze the circuit, we consider the output circuit, and I showed you the output circuit V naught is the voltage across R3. And just quickly draw it here again if you want. Why is it come to black again? I'll leave the null offset circuit. This is R4, R3, rounded. So this is the arbitrary potential V. This is V. This is your A2. So equation 1, it tells us V naught is V, the drop across here, plus the drop across here. So this is V. The drop across R4 is I into R4. So that's how I get V naught is V plus V by R3 is the same as I. The same as I. I is the current that passes through here. And this current must come through here. So we get V outside, you get that equation. And then you can rearrange this second equation in this form. So next we go to determine V. So V, we start from the base of the first transistor. So now we've got two transistors. And then this is grounded. So this is your A, B, C. So this is your VBE1. This is your VBE2. So KVL to this path over here. So to determine V, we apply KVL to loop ABC. So loop ABC, I start minus VB1 plus VB2 is equal to V. And then from Eber-Moll's equation, for the transistors, we get IC in general is I naught e to the VB over eta VT minus 1. But when the transistor starts to conduct, we get that VB over eta VT is greater than 1. So we can write that IC can be approximated as I naught e to the VB over eta VT. Okay, then if you apply it for the first transistor, instead of IC, we write IC1 is equal to I naught 1 e to the VB over eta VT. Divide right-hand side, left-hand side with I naught 1 and take the natural log. So you get natural log IC1 over I naught 1 is VB over eta VT. Then we can solve for VBE1. So we just multiply right-hand side of 4 with eta VT and make VB the subject. So you get VB1 is eta VT to natural log IC1 over I naught 1. So similarly for the second transistor, everything is the same. We just change, instead of VB1, we use VB2. So VB2 is just eta VT natural log IC2 over I naught 2. So we've gotten the two values of VB1 and VB2. Now we substitute it in this equation 1A over here. Equation 1A says minus VB1 plus VB2 is equal to V. But VB1 is equation 5, VB2 is equation 6. So I'll get minus eta VT, natural log IC1 over I naught 1, plus eta VT, natural log IC2 over I naught 2 is equal to V. Now we simplify 7. So to simplify 7, you make eta VT common. then we reciprocate whatever is in the natural log if it's negative. So the positive side of natural log will just be IC2 over I naught 2, which is the first part of the natural log. And then we transpose IC1 and I naught 2, so it will be I naught 2. Sorry, we transpose IC1 and I naught 1, so you get I naught 1 over IC1 inside the natural log. Next, we'll simplify it by saying that the transistors Q1 and Q2 are matched so that the reverse saturation currents I naught 1 and I naught 2 are equal, so we can cancel them in equation 8, and then we remain with natural log IC2 over IC1. But we want IC1 on top in the natural log because IC1 is directly a function of Vs, as we shall see. So if we make IC1 on top of IC2 in equation 10, we got to put a minus sign outside. So we've gotten what V is. So we've gotten what V is. So V is minus neta Vt natural log IC1 over IC2. So now all we have to look for is to relate IC1 and IC2 is in terms of the circuit parameters. So for that, that's why I drew the circuit again over here. We have to find out what is IC1 and what is IC2. So IC1 is the current here. Is IC1 is IC2. And to get IC1 is very easy. For the input of A1, the positive side is grounded, the negative side will be a virtual earth. So this signal Vs over here will send the current towards the earth. And this current, if I call it I1 will just be equal to Vs over R1. And this current goes and becomes IC2. Sorry, becomes IC1. So this is the same as our IC1. Okay, and therefore, and then so we found out what IC1 is. Next, we got to find out what IC2 is, and I've shown you how to find IC2. IC2 is actually approximately equal to just VR over R2. I've done it earlier on. So we just substitute these results inside this equation 10 over here. Okay, so I've said, but IC1 is just Vs over R1, which is I've just shown you over here. IC1 is just Vs over R1, and IC2 is approximately equal to VR over R2. So if I substitute those ones in 10, I'll get that V is minus neta Vt in natural log Vs over R1. Okay, this is our IC1. And then IC2, remember this equation 10 is here. This is equation 10. So it's natural log of IC1 divided by IC2. But IC2 is VR over R2. So when you put in this equation, R2 will become in the numerator and VR at the bottom. So we've gotten V, the arbitrary voltage in terms of the circuit parameters. So I can get V0 now. So V0 from our first equation, V0 was equal to V into R3 plus R4 divided by R3. Now substitute for this V in this equation. Let's call it 13B. So I'll have to substitute for V here from all of this, from 13. So what I've done, I've taken the minus sign of 13 and R3 plus R4 divided by 3 in front. So I get this first term over here of 14. Then I use the neta Vt and natural log Vs over R1 into R2 over VR, 14. So if you look at this equation keenly, all these are constants, all these constants on the left-hand side of the natural log are all constants. I'll call it constant K4. I'll call it a scalar K4. So all this term on the left-hand side of the natural log, I'll call it minus K4, not K times 4. It's just a K4 into natural log of K2 into Vs, where K2 is R2 over R1 into VR. And if you look at this equation 13, sorry, equation 15, this is equation 15. What's happening? Now that equation 15 over there, that is actually the standard form of your log amplifier. Because we said for a log amplifier, the output V naught is some K1 into natural log K2 into Vs, where Vs is the input. Now, if we substitute for this example, which we were given over here, and we take neta is equal to 1, R3 was 0.5, R4 is 29.5 over R3. So this term over here, R3 plus R4 over R3 is 60. And neta is 1. Vt is 26 millivolts, or accurately here is 0.0259 volts. So left-hand side of natural log will be minus 0.0259 times 60 into natural log of Vs. R2 was 20K, R1 is 10K, VR is 10 volts. So you'll get, if you multiply 60 times 0.0259, you'll get minus 1.544. There's a minus sign over here at minus 0.259 times 60, you get minus 1.554 into natural log of 0.2 into Vs, because Vs into 20 divided by 100, that is 0.2. So that's how we get this one. And if you're told to compute the log to base 10, then you multiply this minus 1.544 times 2.303 to convert it to base 10. So you'll get minus 3.578 log to the base 10 of 0.2. Now, if you do this in the lab, you'll find that for the above practical circuit, it's found that the input dynamic range is typically from 0.2 millivolts to 20 volts. Remember, this circuit will only work for positive values. This circuit can only work when the current is flowing in this direction over here, only positive values of Vs. This circuit will only work for positive values of this. In the CAT, I normally ask people to design a circuit which can compute the positive and negative values of logs. And the students, because they just like cramming, they've never been able to get it, but it's so simple. So this one only computes the positive values of logs, not the negative values of logs. So I hope this is one of the circuits you're doing in class. There's even a better one coming next after this. But we've not completed. So the input range typically is from 2 millivolts to 20 volts, typically. And the output will range from minus 12 volts to minus 2.5 volts. So it computes the logs and inverts the output. You get a negative sign at the output. Now, to use this circuit in the lab, you got to calibrate it. So I've said over here, for the above circuit to be used practically, that is in the lab, it has to be calibrated. The following steps The following are the steps. Number one, set Vs equal to 0. So setting Vs is equal to 0. Let me see if I can get the other diagram, which is bigger. I think it's this one. Oh my God. Wow. This one is crazy. I hope you've been doing this in the labs. Yeah? Have you been doing this in the lab? Have you been calibrating your log arms in the lab? I really doubt it. So in the lab, once you set up the circuit, you can't just start computing the logs. It's not possible. So this is the procedure. So step number one is set Vs is equal to 0. So you go to short circuit this input to the ground. That will short Vs is equal to 0. And if you call this output here, say V1 dash, and you put your scope or voltmeter over here, what should happen? You should circuit the two inputs of the op-amp. So ideally, that output of the first op-amp should be equal to 0. If it is not equal to 0, vary potentiometer P1 until the output is equal to 0. So that is what I've written in my notes over here. I think it's this one. No, it's not that one. Okay. So just read again. For the above circuit to be used practically, that is, say, like in a lab setting, it has to be calibrated. The following steps must be used. Step one, set Vs equal to 0. Then V dash should equal to 0. Means the output of A1 should equal to 0. Since V dash is AD into VD, where VD is the difference, the voltage at the difference of A1, and it is equal to 0, so the output should be 0. If it is not equal to 0, so if this is not so, vary potentiometer P1 until V dash is equal to 0. So I hope that's understood. Okay, so that one we're just it's just this. I ground Vs. So this one I'm calling it V dash. Not in my notes, I'm calling it V dash, not V1 dash. I'm just calling it V dash. So V dash should be equal to 0. If it's not 0, vary potentiometer P1 until V dash is equal to 0. That's because the output of A1 is the difference gain times the difference voltage. Since the positive is grounded, the negative is grounded, V dash should equal to 0. Next, step number two. Set Vs equal to VR R1 over R2. So if that's the case, then if you look at the output equation, we've gotten the output equation. It's minus neta Vt, R3 plus R4, all divided by 3 into natural log. The first term was equation 13, was Vs divided by R1. The second term was R2 divided by VR. So if I set Vs by R1 to be equal to VR wait, let's just go with the notes here. So we set Vs to be equal to Vr over R1 divided by R2. So in this brackets over here, in the first part of this brackets, you get Vr, R1 over R2. I hope there's no typing mistake inside these brackets of mine. Then you just substitute that in the bracket. Let's write this equation again here. I think maybe there could be a typing error just to confirm. In the brackets, I'm getting natural log Vs over R1 and R2 Vr. So we are told to set number 2. Set Vs equal to Vr R1 over R2. So we are setting this term over here to be equal to Vr R1 over R2. So it's okay, it's correct. So if we do that, then we'll get inside the brackets of the natural log, we'll get Vr R1 over R2, then there'll be another R, which is this one here. Okay, that's what was confusing me a bit. So you should get this equation over here. I don't know what number it is. Let's call it 14. So the R's will cancel. This R will cancel with this one. R2 will cancel with this one. Vr will cancel with this one. So what will remain in the brackets will just be 1. The natural log of 1 is 0. So the output voltage should be equal to 0. So that's what I've written over here. V0 should then be equal to 0. And if V0 is not equal to 0, then we vary potentiometer P2 until V0 is equal to 0. All right, so that's the function of the second potentiometer. That's the function of the second potentiometer. So once you've done that, then now you're ready to compute the log. You're now ready to compute the logs. All right, you're now ready to compute the logs because you calibrated the circuit. Now an observation, we can see an observation. So finally, in conclusion, we can say from 14, it is seen that V0 is a function of temperature. It's dependent on Vt. If you look at 14, there's Vt outside here. There's Vt outside here. And so if R4 by R3 can be made to decrease with temperature by using a positive temperature coefficient for R3, such that R3 decreases as the temperature increases, then by suitable selection of R3 and R4, then the whole expression for V0 can be made temperature independent. So if we do that, we make R3 to be a function of temperature. So this is the same equation 14. So instead of R3, I've divided the equation 14, I've divided the numerator by R3. So I'll get a 1 for the first term, and then it will remain with in the numerator, R3, all divided by R3 plus R4. So here, all I've just done is the R3, the R4 are divided by R3 to get this term over here, but R3 is a function of temperature. So R3 can be written as R03 into 1 plus alpha T, where alpha T is the temperature coefficient. and the rest of the equation remains the same. So for your design, you go to solve the differential equation where the output, variation of output with respect to temperature is equal to 0. So you can solve for the required temperature coefficient. So I think I'll stop over there. I've given you a small exercise over here, design for V0 such that V0 is independent of temperature. So you just go to simple differential calculus. So first here, solve it for V0 is equal to 0. So now this is the next circuit that we shall do, which is independent of the approximation for IC2. So this is actually the best circuit which you should be doing inside the labs. So I think I'll stop over there. Did you have another class after this year? We lost Monday class.
Yeah,
we have another
the
class.
right group.
Okay. Okay, then I'll stop over there. I'll stop out there for today.